Hi, everyone. My name is Tim Rupert. I'm from the University of California, Irvine, and I'm here today to talk with you about disordered interfacial features as local equilibrium states capable of modifying nanocrystalline metals. So the work I'm going to tell you about today was really performed on the day-to-day by some great early career researchers in my group. Pulkit and Tianjiao are postdocs, and Charlotte is a recent PhD graduate, and Esther is a current PhD student. So to jump right into the topic, we're really inspired in this work to try to change and improve how we design materials. And what I'm showing on this slide is sort of the traditional way we go about in making the materials that we're targeting. We have gotten very good at using very robust tools to design material phase contents based on thermodynamics. Just as an example of this, this is showing a material made with additive manufacturing. And what was really they were trying to do was connect an INVAR base to a TI64 top through a gradient section that could try to sort of, match maybe thermal expansion coefficients or something like that. And if you do something like that, you can go through this vertical structure and go and predict how you would have different, if you know what your changes in composition are, what you would predict your different phase transformations you go through in that region. And for example, you could pick out a region and predict at some point through there that you should have some combination of phases, go and check that with electron microscopy. And in this case, trying to confirm that you have HCP, B2, and C14 type structures, you can confirm that that works. We've gotten good at that, but we're unfortunately not so good at the second part. So often when we think about microstructure, so how these phases are arranged, what are the grain sizes, what's the texture of the material, we don't really have a way to design that. Instead, we just try to trick our system to have some sort of microstructure that we might target. And I'll use examples from my area, which is nanocrystalline materials. Often we're trying to make materials with smaller grain sizes. So we do things like high pressure torsion or equal channel angular pressing, where we can control the number of turns we put the sample through, or the angle that we extrude this through to try to change our microstructure. If we do things like melt spinning, we'll try to be controlling the rate at which we cool from a liquid state. If we do sputter deposition, we're often controlling our substrate temperature, deposition rate, things like that. They're not directly able to tell us what our grain size would be, but maybe we just sort of hope and mess with these parameters so that we can trick our system. We'd really like to do is be able to design in the same way microstructure like we can phase content. And I'm optimistic. I think we can get there. And a lot of that optimism is really based on some huge advances we've had in stabilizing nanocrystalline materials. The real key innovation here is the idea that not just the phases, but also the defect structures can be treated as separate thermodynamic entities. So if you think of a grain and grain boundary combination system, you can think about what are the thermodynamic parameters that describe the grain interior and also the grain boundary itself. Using these types of tools, people have been successful in finding stable nanocrystalline alloys. An example could be seen, this work from Chris Shu's group, where they were after this idea of making a stable tungsten-rich alloy. They could go and look at all the possible dopant or alloying additions they could use, predict that titanium would work very well, and then they went through the process of making this and testing it and showed that it was stable. In addition to just reducing the energy of the defects and maybe stabilizing a grain size, you could even think about tuning and controlling the structure of defects. One way to see this is in this really beautiful set of bicrystal simulation data from Frolov, Asta, and Mission. And what these authors were doing is they're looking at the same boundary and they're increasing the composition. And at some point, so as they increase that composition, the grain boundary excess goes up. And at some point, they get a discontinuity and then follow along another path. And that's really a sign that they had something that looks like a phase transition happening inside of that boundary. In this case, it's going from a single layer of segregation to a bilayer of segregation. These transitions can be called complexion transitions. And the idea is just as simple as thinking of the defect state as something that can be predicted and described with thermodynamics. And if you do this, you can start to see lots of different options, even just in metallic systems. So you can have clean grain boundaries. These are our traditional grain boundaries, just no change in chemistry, just different crystals put together in different ways. You can have boundaries and interfaces that are chemically distinct, in these cases with different segregation patterns. And you can also have discrete layers that form at the interfaces. So in my group, one thing we've been really going after is that last one, that having discrete layers, and trying to make layers that are disordered or amorphous. I'm going to briefly go over how we actually make these things. So the way we do it is with mechanical alloying. We can make a nanocrystalline microstructure with a sort of given alloy composition that we target. We heat up to allow for segregation to the grain boundary to occur. But usually we heat up high enough that we can get a pre-melting transition at the boundary. So the boundaries become disordered. And then if we very rapidly quench down, we end up freezing in some of these amorphous or disordered grain boundaries. And we can contrast that with the same set of samples, which are slowly cooled down and then only have the ordered interfaces. And we have lots of evidence that these things are beneficial for properties. That's not really the focus of what I'm going to talk about today. But for example, we can see that these amorphous complexions can make our materials stronger and more ductile at the same time. We can use them to fabricate bulk pieces of these nanocrystalline metals. And then we can also make these materials more radiation tolerant. What's shown here is some in situ ion irradiation of the TEM in collaboration with some of our good colleagues at Sandia National Lab. And the blue curve is the amount, the sort of rate at which you build up defects inside of the grain structure during ion irradiation in the ordered boundary sample. And then the red one is same exact microstructure in every other way, except it was quenched and we have those disordered films. And we can see a pretty appreciable difference between those two curves. So, I'm going to start talking a lot about grain boundary structure and things like that. And it's important to understand why I care about that. So I mentioned that we can get increased strength and toughness. And one of the mechanisms we care about is how the interfacial state affects the absorption of dislocations, because that turns out to be really important for failure of these materials. When you have ordered boundaries, this is showing a relatively simple simulation cell where nucleating dislocations in the middle and they're coming out, hitting the boundaries and being absorbed. You have to accommodate that plastic strain into a relatively small volume, fraction of a nanometer where this ordered boundary is. You contrast that with if you go to a thin amorphous complexion or a thick one, you can start to accommodate that plastic strain in a larger volume. What that means in terms of properties is you can absorb more dislocations and your bulk sample can accommodate more plastic strain. What I want to talk about today is some of the descriptors that we can use to modify this type of behavior. I mentioned this idea of thickness of the complexion being important, and it turns out that we've seen a direct correlation with that. So that the thicker the amorphous complexion is, the more dislocations we can absorb before fracture. Okay, basically it gives it more more room for these shear transformation zones to be active. We also think that short range order, the structural short range order within these amorphous complexions is really important. And a lot of our motivation for looking at that is what people have seen in the metallic glass, which you can think of as an analog of taking that amorphous complexion and thinking about how it would behave in the bulk state. And it turns out that the short range order motifs of packing are very important for the plasticity in metallic glasses. This is showing an example of a simulation where these dark regions or red regions are regions where you have clustering of full icosahedral packing. And it turns out that those end up being sites where you can end up finding plastic events start to nucleate and occur. And there's even been some studies about how this short range order can be important for this dislocation absorption event. This is from a group at Iowa State where they're looking at dislocations absorbing and the disruption of the short range order in that disordered film. So my goals for today are to really talk a little bit about two important topics. I'm going to talk a little bit about trying to understand the nuances of the internal structure of these amorphous complexions. So they're disordered, they don't have long range crystalline structure, but they're not featureless. And to do that, we're going to look at atomistic modeling in copper zirconium alloys. And then we're also going to talk about how we can try to vary these descriptors. So how can we modulate the thickness and short range order distribution inside these amorphous complexions? And we're really going to look at some experimental processing studies in both copper rich and aluminum rich alloys. So jumping into that first one, I'm going to show some simulation data. The setup is relatively simple. We look at some bicrystals. So, grain 1, grain 2 interfaces here. And we're going to use a set of hybrid Monte Carlo molecular dynamics simulations to change maybe the temperature composition of the system and find the equilibrium structure of the interfaces in those cases. This is just showing an example of what you can get as you add more dopant to the interface or to the system. It goes to the interfaces, reduces the energy of the system. And for example, you could see that as at a given temperature, if you increase the zirconium content, you can get thicker amorphous complexions. We're actually going to do a slightly different set of simulations. We're going to keep the global concentration the same. It's going to be 2 atomic percent zirconium for this simulation cell. And what we're going to do is we're going to vary temperature and crystallography to understand how internal structure changes. And we're going to look at a whole set of different boundaries. All these details don't matter all that much right now. We'll dig into some of the details in a minute. But basically, for now, we can think about the idea that we're looking at a set of symmetric and asymmetric boundaries to try to look at different crystallographies. And we're also going to look at different temperatures. So 2 of these temperatures are below the melting point of the bulk system. So we're trying to find what I would say is a real complexion. So the crystal is solid, the interface pre-melts, and it finds a local equilibrium state. Just for comparison, we're going to also make a wetting film. So we can do all kinds of fun tricks in atomistics. We can try to freeze everything and just go to the interfacial region and melt that. So just locally raise the temperature above the melting point, find a structure, and then we'll compare that with this complexion structure. The tools we're going to use to look at structural short-range order is Voronoi tessellation. The basic idea is pretty simple. If we have a collection of atoms, you take this atom and you find the boundaries of space that's closer to that atom than any other one. That's its Voronoi cell. And then you just describe that cell. And one way to do that is by listing the number of faces with I edges, okay? And just for reference, for example, if we're looking at perfect FCC, it's going to be 0, 12, 0, 0. You can actually see that if this is looking at one of these complexions, we're looking at those atoms which appear green here. Those are this 0, 12, 0, 0 structure. That's just FCC. It's a more complicated way of describing FCC in this case. But the nice thing about this is to capture other nuances of structure. So for example, we can look at a complexion and also a bulk metallic glass and start to see the structural motifs that come out. So I'm going to first go to this metallic glass. So these light and dark blue motifs we see, 0, 0, 12, 0, and 0, 2, 10, 0. One of them is the full icosahedral packing, and the other one is something that's not quite exactly that, but it's very, very close. And we can say is that if these are the most common in the bulk metallic glass, these probably say something important about that structure. And in fact, we see some of those same features and motifs in the interior of the amorphous complexion. But you'll notice that there's some other colors that pop into this figure. So the red and the orange atoms that light up have different structures, and they're much more ordered. So 0, 10, 2, 0, and 0, 8, 4, 0, these look quite a bit like that perfect FCC. They're a little bit distorted, but they're pretty close to that structure. So for the rest of my talk, I'm just going to try to simplify this so we don't have to remember all these numbers. And I'm going to call the icosahedral and the near icosahedral disordered polyhedra. And I'll call the types of Voronoi cells that are similar to FCC ordered. Okay, just put it in 2 bins so we can be a little bit more streamlined. When we do all of this, we also have been careful to try to understand the effective cooling rate to the extent that we can do that in an MD simulation. And I'll come back to that in a little bit because this is something we're going to explore more thoroughly in experiments. Okay, so on the bottom right here, what I'm showing you is a bunch of plots. We've worked across those grain boundaries under these different temperatures. So low, medium, and high. So this is truly above the melting point. And we can start to see some trends that pop out. One thing I'll point out is that we don't see huge differences with the cooling rate. And this bears out. It's just sort of the fact that we can only access certain cooling rates with MD. But we start to see that the center of these complexions looks very different than the edges. So those gray areas I've marked out have 0 density of these disordered polyhedra, but start to have these peaks in the ordered polyhedra there. So that's one way we can start to see that the amorphous crystalline interface is different than the interior of the amorphous complexion. But another thing we notice is that those peaks on either side are not symmetric. So in this example I've pointed out, it's much higher. It's at 35, 36% ordered on the right side and only at 25% ordered on the left side. Right? So we're going to start to look at that ordered short range order as a metric of what's happening at those amorphous crystalline interfaces. And we can start to compile some data. What I'm showing you is just collecting all of those descriptions of the amorphous crystalline interfaces for that same boundary I just showed you. And again, I'll point out that the cooling rate doesn't seem to have a big effect within a given sample. But this gap between the ordered short range order density on either side does seem to be very dependent on the temperature at which I made that complexion. So the low temperature complexion has this big gap between these two sides. So the filled data points are on one side, the open data points are on the other side. That gap gets smaller as we increase the temperature. And then in fact, when we look at wetting liquid film, there's no gap whatsoever. So that asymmetry goes away. So we can start to identify this idea that the artificial amorphous film doesn't have the asymmetry. And that tells us something important. It means that that asymmetry is something fundamentally related or fundamentally core to the idea of a complexion truly being in equilibrium with the crystals next to it. Okay. Start to put the data together for the different grain boundaries, and it's looking at very similar data. Here, we're just sort of removing the cooling rate since we found it wasn't a dominant feature. And what you'll see is that look at these different sets of points. So again, filled and open are different sides of the boundary. On the left here are all symmetric boundaries. And what you find is that, okay, there's no difference between the two sides. The crystallography on either side of the two crystals is symmetric. So the amount of short range order we have at those amorphous crystal interfaces is symmetric. That falls apart when you look at the asymmetric boundaries. You start to see that, at least for the complexions, you never get that these points right next to each other. There's always some gap that seems to be important. Just to make it a little bit easier to see, what we're plotting down here is the delta short range order density. So what we get at amorphous crystal interface 1 minus amorphous crystal interface 2, they're all near 0 for the symmetric boundaries, and they're non-zero for the amorphous complexions in the asymmetric boundaries. But there's other interesting things on this plot that I'll take a minute to point out. So one hypothesis I had when I first saw this is I said, okay, that makes sense. The asymmetry and the symmetry come through. I suspect that the amount of short range order we have at either side is really dependent on which crystal is nearby. But it turns out that that can't be the case. And I can prove that to you because these two open circles right here are next to the same grain. There's a grain which terminates at a 110 face into that amorphous crystalline interface. So if that were true, we would expect these to be at the same level. And instead, they're very different. Okay, so that tells us that something more complicated is going on. And our next step up in making a more complex hypothesis was that, well, it's not just the grain next to it. It's the two grains and overall the whole system, grain 1, complexion, grain 2, how they work together that determines the structure. We thought for a long time about how we could understand this, looked at some of the work on trying to describe the thermodynamics of these features, thinking about how you have to create new interfaces. There's an energy penalty for having that amorphous structure. And we really came to this idea that these confining crystals should contribute to this process. And the way we started to think about how that would happen is it might have something to do with relaxations that account for the difference in crystallography between the grains on either side. And one way you can kind of see this is to just look at the grain boundaries that we're studying before we allow the complexion transition to occur. So these are undoped boundaries. It's just looking at the crystallography. And on the left side here, we have a symmetric boundary. On the right side, we have an asymmetric boundary. If you look at a boundary like this, you can go and look, for example, at the local atomic volume and start to see where there's some mismatch between the crystals. So for example, a place where the crystals don't line up very well, you start to get these bright regions. So the black is the value for the crystal interior. These are high atomic volume regions. But if you look at that symmetric boundary, it's symmetric on either side. So where you get bright red on one side, you get bright red on the other, okay? And that's very different than this asymmetric boundary where you have it seems to be more coloring on this right side. And also it's not in the same locations, okay? And we started to think about how we could try to capture that. And what we did is we said, well, let's look at these regions and try to define what's happening in grain 1, what's happening in grain 2. And the way we did that is we said, just a really simple idea, let's take the percentage of high volume atoms. So anything that's above the crystal interior value, and we'll take that percentage. And for example, in the symmetric boundary, it's 55% of the atoms, but it's 55% on either side. In contrast, for this asymmetric boundary, it's 60% and 72%. So you start to get an asymmetry in describing how those grains are accommodating their mismatch, right? And if you do that, you can start to plot some data. Again, this is not for the transitioned boundaries. This is just for the pure systems, and start to look at how the grains accommodate each other. And this is same type of plot showing the different asymmetric boundaries, and this time plotting the percentage of high volume atoms. And I'll look at those same 2 points I did before. So 2 grains that are terminating in the same crystallography, the 110, okay? And now you can start to see a difference. So even though that crystal is oriented the same, it's mushed up against a different oriented crystal. And because of that, it has different sort of local strains and local regions of high atomic volume. So we think that might be getting us down the right road where we can understand how these grains are accommodating each other. And what's great is that we can start to test this idea. So I'm showing some pretty complicated plots. We're trying to plot, okay, what's either the ordered, short range order density at the amorphous crystalline interfaces. This is looking at individual sides, treating them separately. And then also the change in the ordered short range order density. So this is that asymmetry amount. And then on the bottom, we're having some signature of just the crystallography. So again, the grains before the grain boundary system before we dope it, what's the percentage of high volume atoms in that grain near that amorphous crystal interface? And then also what's the change, right? And you can tell very quickly that on this left side, there's not great correlation. It's a horrible fit to this data. And what it tells us is that the number of high volume atoms, again, doesn't describe the amorphous crystalline interface. But on the right, the data collapses pretty well. And this tells us that, again, we need to think about the difference in crystallography to understand the structure of this feature. And we can't just think about one amorphous crystalline interface and that grain. We have to actually think of this whole system. Now, I want to finish by mentioning that on this point, by mentioning that this correlation, the fact that it's inverse, actually makes a lot of sense. So it tells us that when we're considering these two grains as a system, the grain that has a larger percentage of high volume sites, so I think of it as it's more mismatched, or it's more incompatible, that one ends up having less of the ordered short range order. So it looks more like a sort of truly random glass. The one that isn't deformed and isn't out of whack, looks more ordered, and it's capturing that order of the crystal next to it. Now, one natural question is this just, you looked at a few bicrystals, are you sort of making something out of nothing? Way we can test this hypothesis is, we've done other studies of complexion transitions in polycrystals. Let's take a sample like this, which has many, many grain boundaries, and let's do the same type of analysis. Let's take and look at, okay, what's the crystallography before we dope it? We can go and find the local atomic volumes and find what percentage are higher than the mean or higher than the bulk value. And we can also identify those ordered short range order motifs. These are just the atoms that have that structure highlighted in black here. And we can go out and pick out all the boundaries that transition to amorphous complexions. What do we see? The exact same trend. So it has that same inverse correlation. These are totally different boundaries, okay? And they're not sort of high symmetry, anything like that. They're totally random orientations. Okay, so now that we've started to learn a little bit about that distribution of short range order, we understand how the amorphous crystalline interfaces are different. What we've now been pushing to do is see how we can change both the short range order and also the thickness of these amorphous complexions. So I'm going to jump into some experimental studies to finish up. Again, going back, we make these materials with ball milling. When we heat it up, pre-melt the boundaries and quench down, we see these amorphous complexions, but I didn't mention before, and I want to point out now, that although we find them within our microstructure, they're not all the same thickness. So we get different thicknesses within our microstructure. And for example, for a copper zirconium alloy, we'll find that we'll have some distribution. Some boundaries are ordered and haven't transformed. And then we get a distribution of thicknesses that can be 1 nanometer, 2 nanometers, up to about 5 or 6 nanometers. So there's some variation inside of that structure. One way we're trying to see how we can modulate that distribution and what it looks like is by increasing the number of elements in the boundary. So that copper zirconium system I just showed you, it does an okay job at satisfying some design rules we've come up with. It lets you're adding something that segregates the boundary, and copper and zirconium have negative enthalpies of mixing. But if you truly wanted to make a system that was really optimized for amorphous complexions, you would also want to have 3 or more elements and large size differences. So the first thing we're going to do, we're not going to worry so much about the size differences right now. We'll come back to that in a second. We're going to dive into adding more and more elements. So I'll show you going from a binary to a ternary alloy. So instead of just copper zirconium, we're looking at copper zirconium hafnium. This is just showing that, again, we have segregation of these species to the boundary. And then also we move to a quinary alloy, copper zirconium hafnium niobium titanium. In this case, the crystals are really just pure copper. And then we end up getting segregation to the interfaces. Now, part of the reason I'm showing this data is, although we hypothesized that these 4 elements would go to the boundary, it turns out that only 3 of them did. So the boundary has some residual copper. It also has niobium, titanium, and zirconium. But in this alloy, those other elements went and covered up the grain boundary sites, and the hafnium actually went and formed carbides elsewhere in the microstructure. Okay, so I just want to point out that this one actually has, in the grain boundary region, 4 elements. But we can go and repeat those experiments, measure the distribution of complexion thicknesses, and what we can see is a really interesting trend. So this black data is our binary, the gray is our ternary, and the blue is our sample that has a quaternary composition with the boundaries. So as we go from 2 to 3 to 4, we go from an average complexion thickness of 1.7 to 1.85 to 2.44. So as we increase chemical complexity at the grain boundary, we monotonically increase the complexion thickness as well. We can do even better if we can satisfy that 4th design criterion. And we have been doing this in some aluminum-rich alloys. So I'm going to show you aluminum plus either magnesium, yttrium, or nickel, and magnesium, iron, or nickel, plus some yttrium. Okay. And one thing is mentioning is we're working with these things not in the powder form, but we're consolidating into a bulk form. So what's pretty cool is we actually don't even, this sample is so good at forming those amorphous complexions and sustaining them that we don't even have to rapidly cool it. So we make this in a relatively simple hot press, and then we just turn it off and have to let it cool down. And it happens over a few hours, about 4 hours. And if we just do that and we go in and look afterwards with TEM, we can go and find amorphous complexions in our microstructure. So that never happens in those binary copper alloys I showed you before. And in fact, if we really want to see what the comparable state is, we would go and take that same pellet, we'll heat it back up to the same fraction of the melting point and quench it down. It's nearly identical to what we did in the copper. And there we find really, really thick amorphous complexions. So in this case, we're regularly seeing amorphous complexions that are 8 or 9 nanometers thick. Okay, so that confirms this idea. We see it in the copper, we see it now when we move to the aluminum, that if we do proper alloy selection, we can increase the amorphous complexion thickness distribution. We also think that this is going to be a promising route for tuning the short range order within the amorphous complexions. And I didn't show this before, but this is some of that simulation data. And this time we're plotting grain boundary zirconium content through those complexions. And one thing you notice is that in those regions where you get more ordered motifs in the amorphous crystal interface, you also see a decrease in the amount of zirconium. Okay, and that tells us that the amorphous crystal interfaces have a different composition than the complexion interior as well. And we're trying to modulate that. So I'm just showing a very recent result from copper, zirconium, niobium, titanium. So we've gotten rid of the hafnium because it was doing its own thing. And what we find is quite interesting. So there's 2 copper grains here, zirconium enrichment at the boundary. But if you look at where the niobium and titanium starts to enrich, it's at the interfacial region, but it's not uniform. It's actually on the outsides of the grain boundary. And I'll just draw some lines to guide your eye. So we'll go right outside the region where the zirconium is highest, you start to see that the niobium is highest along those interfaces, and so is the titanium. So basically, these regions which are gray are being filled in by the niobium and titanium. And we think that we can use this type of effect to control the short-range order. You get all kinds of interesting compositional patterning like this in those aluminum alloys as well. On this top, we're just showing that you get segregation to all the grain boundaries. You can get some amorphous complexions. These here are outlined by the yellow lines. But what's interesting is the amorphous complexions end up having enrichment of yttrium and nickel along the outside as well. Primarily, it's most obvious in the yttrium in this case. That actually is, we think it's important for controlling the complexions, but it does lead to other interesting stuff. So in this case, you actually form the growth of nanorod precipitates from the amorphous complexions. And those sort of decorate the inside of the microstructure. And they can also eventually lead to nucleation of real secondary intermetallic phases. Okay. And on the bottom here, I'm just again showing that that clear sort of core shell structure, where in this case, those little nanorods are actually aluminum carbides, but they collect magnesium and yttrium along the outside. So one of the questions we're digging into, I don't have the answer for you today, is how does this compositional patterning within amorphous complexions end up altering the short-range order distribution? And I'll come back to that at the end and show you how we're trying to poke at this in experimental standpoint. The last thing I want to mention is the effective quench rate on these types of features. So when we make these bulk samples, we can actually go through an interesting experiment where rather than just dump the whole thing in a bucket of water, we end up putting the hot sample on a heat sink so that it cools very fast at the bottom and much slower as you go vertically into the sample. If you do a little model of this, you can think about as a fast quenched, medium, and slow quenched region. You can do some analysis and understand what the temperatures are. These details don't matter, but the main point is that you're getting large variations in both cooling rates, but also the time to critical temperatures. So if you think of you have to stay above a certain temperature to keep your amorphous complexions, the time it takes to get below that changes in these different regions. And that can turn out to really modify the distribution of complexion thicknesses we measure as well. So before I showed you change in distribution with composition, here I'm showing you how the quench rate affects it. So the fast quench region has the thickest complexions. And as we slow down how fast we quench, we start to move back to thinner and thinner values. And what that tells us is that as we cool slower, we're having some amorphous complexions that were there at high temperature are transitioning back to ordered boundaries. And that's quite interesting. So we're really seeing almost some evidence of what's happening on a grain boundary TTT diagram, which I think is pretty cool. You can start to see the overlap of the quench rate and the composition if we just compare the binary and the ternary copper alloys. So although we see variation for the binary, if we do that same experiment for that ternary alloy I showed you, we find that the distribution of complexion thicknesses fall right on top of each other. So going back to that TTT diagram, although we hit and have transition back to ordered boundaries for the binary alloy, the ternary alloy, this transition region is pushed out to the right, so so longer times, and we don't have that transition. And this is, you can actually find an analogy there in what people have done in the glass literature. So in theory, you could make an amorphous material out of any metal, but if it's a pure metal, you have to cool down unrealistically fast. And the way you actually get bulk metallic glasses is not that you cool faster, you make a better alloy, and you go to a marginal glass and a bulk metallic glass that you can cool at sort of traditional or regularly accessible cooling rates. So just for reference, if we go and try to analyze this, try to do some estimates, we can estimate that this ternary can be cooled at the very least 1,000 times slower and still maintain that high temperature complexion distribution. So we're now trying to poke at this and how we can use those cooling rates to alter the short range order distribution within our samples. The last slide I want to show you is kind of an idea of how we're trying to get at that. It's really hard to measure short range order experimentally. We can't do the same thing we do with our atomistic models, but there's some promising work in the metallic glass field that's motivating us and inspiring us. This is just showing one example of nanobeam electron diffraction. This is an in situ TEM testing of metallic glass samples. And what these authors were doing, this is from Andy Miner's group, is they were rastering around a stress concentration as they cooled on the sample and taking these little nanobeam diffraction patterns. And what they could get is a lot of signal for either twofold or fourfold symmetry, which they were sort of arguing as a sign of local order inside of that material. And they could see how that local order was disrupted as a shear band forms around that stress concentration. We're trying to do the same thing inside of our amorphous complexions. So this is very new data, like from a week or two ago. There's an amorphous complexion here, and we're going across it doing a nanobeam diffraction experiment. And I'm just pointing out 3 different spots. We have a whole array of this data, but you can see the interior of that amorphous complexion, this center region is what you really want to look at, is largely featureless and doesn't have much symmetry. In contrast, if you look all the way over at the other grain, you can start to see some symmetry that is associated with the order inside the crystal. And the amorphous crystalline interface is somewhere in between that, okay? We're still figuring out how to analyze that, how to extract out this data and connect it to what we see in the atomistic models, but it's definitely showing us this qualitative trend. And what we really want to do is connect this to those atomistic models. So if we can go and see how virtual diffraction patterns are affected by these different short range order motifs, we can go and really understand these nanobeam diffraction results more clearly. Okay, so with that, I want to leave you with a few take-home points. The first is that the structural short range order in amorphous complexions really depends on the confining crystals. And that's really important because it tells us something that's really fundamentally exciting about complexions. They are not just some different structure that happens to be at a grain boundary. This is a complete system. This is truly the 2 grains in the interfacial region finding a local equilibrium. We're poking around at how we can use alloy chemistry and cooling rate to affect the descriptors of these complexions. We've been able to show pretty clearly how they can affect the thickness of the complexion distribution. And our current efforts are really trying to understand how those short range order gradients could be modified by running some relatively difficult diffraction experiments. Thank you very much for your attention. Hope to see you all in real life at a conference soon.